The nuclear reactors across the world are quietly generating electricity for billions of people. And most of that power still comes from conventional water-cooled reactors. For decades, these reactors have been the undisputed backbone of the global nuclear energy grid. But behind this success story lie some long-standing challenges that the industry has never fully solved. So, the question is, what if there was a fundamentally different approach? That's where Copenhagen Atomics, a Denmark-based company, comes in. They're developing a Thorium Molten Salt Reactor that aims to address many of these challenges from the ground up. But how exactly does this technology work in practice? To find out, we sat down with their CEO, Thomas Jam Pedersen, to explore what makes their approach different and why it could matter for the future of energy. Let's get into it. Before we dive into the technology, let's introduce the mind behind it.
I am Thomas Jam Pedersen. I'm one of 4 co-founders of Copenhagen Atomics. I'm also the CEO, and I have a background in electrical engineering.
Most SMRs rely on established light water technology. Why did Copenhagen Atomics choose to pursue a Thorium Molten Salt Reactor instead?
Yeah, so Copenhagen Atomics is started by 4 people. None of us were from the nuclear industry when we started the company. We looked at the old nuclear industry, sort of with light water reactors, and said, this is not a great technology because it can only use maybe a few % of the fuel, and then it has to unload the fuel, and then there's all this problem with spent fuel or unused fuel or whatever you want to call it. And through some research, we realized that with a Thorium Molten Salt Reactor, it's completely different. You can use all the fuel, or almost 100%. And this creates much less waste, and the fuel form thorium is like 1,000 times less expensive than the uranium we use in the traditional reactor. So we started asking ourselves and everybody we met, why are we not using Thorium Molten Salt Reactors when it has all these benefits that the old reactors doesn't have? And some people were trying to answer that, but we wanted to find out sort of how difficult it would be technically to make a molten salt reactor. And so in the beginning, we're just experimenting to figure out, is this something that will take 2 years or 20 years or 200 years? And we saw that it's definitely less than 20 years, but maybe more than 2 years.
Given that your MSR operates in a thermal neutron spectrum, how do you justify its waste-burning claims compared with fast-spectrum designs?
Oh, that's a good question. Yes, because a lot of people that were studying to become a nuclear engineer were told back in the old days that you need fast reactors to burn spent fuel. And that's because spent fuel consists of a tiny amount of uranium-235 and then a very large amount, 95% uranium-238, and then some transuranics. And the way people talk about that is you want a reactor that can burn the uranium-238. But uranium-238 is the exact same as what you dig out of the ground when you mine the uranium, so it's not dangerous in any way. It's basically a natural substance. The thing that causes spent fuel to be toxic, both in terms of chemical toxicity, but also in terms of high radiation, is the transuranics and the fission products. And of course, you cannot burn the fission products. That's the exhaust. But if you could burn the transuranics, then you end up with a waste form that is much simpler to deal with. So in a Thorium Molten Salt Reactor, you can actually burn those transuranics, and they burn better than in a light water reactor or the traditional thermal reactors. And that's why now you can actually burn spent fuel in thermal spectrum. But of course, you cannot efficiently burn the uranium-238. For that, you need a fast reactor. And that's why people talk about fast reactors. But they got the whole thing wrong, because why would we want to burn natural uranium? There's no economic benefit to doing that. That's why you need a Thorium Molten Salt Reactor, because then you can burn all the nasty stuff, the transuranics and the plutonium, and you get a lot of energy at a low cost.
Getting a breeding ratio above 1 in a thermal spectrum reactor is a major challenge. How do you plan to make that work?
Yeah, so When we design reactors in the nuclear industry, we use simulation tools for figuring out the neutron economy of each different reactor. And over the years, these simulation tools has gotten better and better. Back in the 1960s, they were not very good. But anyways, the computers we had back then were also not very good. But after sort of year 2000, they got better and better. And today they're really good. And this means that we can fairly accurately simulate how the reactor behaves. And therefore, we are also fairly sure that it works. I mean, there's sort of not a big doubt whether it works or not. It's more of a question, is there some part of the design where the regulator wants to put in some extra safety margin that is different from the simulations we've made? And if the regulator wants to put in a large safety margin in one respect or the other, that might cause the neutron economy to change. So I'm like 99% sure that the reactor will work as we claim with the breaching ratio from a technical point of view, but there's no way for me or anyone else to know exactly what would be the requirements from the regulator, because nobody has gotten this type of reactor approved before ever in human history.
Most reactors are designed to run for 40 to 60 years. What limits this reactor's operational lifespan to just 5 years?
Yeah, that's a good question. Why 5 years? So, of course, if you want to run a nuclear reactor for 5 years, the regulators and everybody else, I mean investors, they would want to know, okay, so how much did you test this before you got started? And if you only test it for 1 month maybe, then it's a little bit difficult to come and say, but we want a license for 10 years. So we think we would need to test maybe 1 year before we can get a license for 5 years. And it's sort of reasonable to do a 1-year test reactor. But if you wanted to get 20 or 30 years, and you would have to test maybe 5 or 10 years before you get the license, it would just take too long before we get a commercial license, and it would be not economically advantageous to do that. So we need to start somewhere, and we thought that 5 years was reasonable, both from sort of a return on investment point of view, and also a reasonable amount of time of testing compared to the runtime of the commercial reactor. And finally, the materials also get degraded over the years. And the longer you want to run, say 20 or 30 years, it's much more difficult to predict how much degradation there will be on the materials. But if it's only 5 years, you can give fairly good predictions on the behavior of the material. That means it's easier to get a license, and you will spend less years in the licensing process. So essentially, the 5 years is picked for sort of a pros and cons of a long and short period. And of course, once we know more, we can either extend that, so make it more than 5 years. But actually, as it looks right now, it might be more advantageous, instead of making it longer, instead run at higher temperature, because that's also something that degrades the materials. And I think that's economically more advantageous. So I think as soon as we reach 5 years, then we will try to increase the temperature, slowly making higher and higher temperature. And that would also require some testing.
So if the reactor core and activated components are replaced every 5 years, how do you justify this in terms of maintaining a competitive cost of electricity and managing radioactive waste generation?
Yeah, that's a good question. So when we replace the reactor every 5 years, the fuel, I mean, that's typically what people talk about as waste, because of the old reactors. The vast majority of the waste there is spent fuel. And so in our reactor, it's completely different. We don't discard the fuel after 5 years. We continue to use the same fuel for 100 years or more. So the fuel form is not a waste form. But of course, the sort of the used reactor container is a waste product. And it is radioactive in the beginning, but it's much less radioactive than spent fuel from classical nuclear reactors. But of course, it's too radioactive that you can sort of just put it back in recycling right away. So it needs to cool down from radiation in the first couple of decades. And then after a couple of decades, you can recycle that reactor container, which is made mostly from steel, stainless steel, copper, different metals. and those metals can be recycled basically by remelting them in a big furnace, and then they can be reused either for other reactors or for pilings or bridges or whatever it might be. So the vast majority of the reactor material can be recycled. There will be some small amount, a few percent, that we need to send for low-level radioactive waste.
In your reactor design, what component ultimately limits the system's operational lifetime, and what degradation mechanism governs that limit?
Yeah, so it's definitely a reactor core. So the amount of neutron radiation in the reactor core is probably 1,000 times or more higher than anywhere else in the whole reactor. So those plates or materials, wall materials inside the reactor core, they see a huge amount of neutrons, and that damage, that basically makes the wall material brittle, and that's the majority of the degradation. And actually, I want to explain, so each atom in the wall, all the atoms, there's trillions of atoms in a wall like that, and each atom moves 10 times throughout the year. So it's even though it might look like steel, it's not really steel because it's moving around like crazy. All the atoms change and get a new location several times throughout the year. And that's because of that neutron radiation. And not all materials can sustain, most materials actually cannot survive in that radiation. But we've found a number of materials that can, and when I say find, it's not that difficult because it's the same materials that are used in all the other reactors, including fusion reactors.
What design or material solutions are you pursuing to increase the service life of that component?
Not really. We really have to focus on getting a first commercial reactor up and running. And then once that's running and once we've gotten the price down, it's more important to get the price of the electricity down to a level where we can honestly outcompete anyone else. And then after we do that, then we can maybe look at extending the lifetime of the materials. But people who do material research know that a lot of times it takes decades to make new materials. So that's not an easy problem to solve.
Thorium breeders are said to be proliferation-resistant. How does this hold true for your reactor?
Yeah, so that's true. Molten salt reactors, and especially Thorium Breeder molten salt reactors, are very resilient against proliferation. Proliferation meaning, can you use these materials for military purpose or weapons of mass destruction? And the thing with thorium is that once you convert the thorium into uranium, then you also generate an isotope called uranium-232. And uranium-232 has a number of daughter products that are highly radioactive. That means you can basically not handle this material easily. You cannot handle it in glove box, you cannot handle it in your bare hands or in a normal workshop. So it's super difficult to convert that material into something you would use for a bomb. And that's exactly why all the nuclear bombs we've ever built in the whole world was not made through this process, because it's way too difficult. So it's easier to use enriched uranium or plutonium-239. And that's what all the countries that wanted to get nuclear weapons did. And I imagine this will continue, and that there's no reason why they would try to do it the most difficult way. So that's the reason why Thorium Breeder reactors are more safe.
What physical and pyrochemical methods are used to strip fission products from the molten fuel mixture?
Yeah, so we are still taking some patents in this area, so I don't want to reveal all the secrets, but some of the things have already been done. So let's first define it for the audience. People who talk about fission products typically divide them into 3 different categories. There's the noble gases such as xenon and krypton. That's one category. Then there's the lanthanides. Those are also the same as rare earth elements. They are notoriously difficult to separate. That's also why rare earth is expensive, rare earth materials that we use in the industry. And then there's all the remaining other elements in the periodic table. And sometimes people also divide that third group into different subgroups. But in general, you can say the first group, the xenon and krypton, the volatile fission products, they can actually bubble out of the salt, just like pops out of your soda pops. They basically separate themselves, but you need to make special systems to handle those. They are still radioactive fission products, and they will decay to other isotopes once they're outside of your fuel salt. So it's not, even though they are easy to get out of the fuel salt, that you still need special systems to handle them and so on. But I think we've figured that out. I mean, that we're not too much in doubt of how that will work. And we are already separating most of the other impurities from our salt. So remember that we already have ton-scale salt production here at our facility, and we buy huge amount of salt from chemical companies, and when they supply that to us, they have impurities, and we need to remove those impurities. So this is something that has been going on for many, many years, and we will continue to improve those processes of how to remove impurities. And of course, doing that, there's some of the elements that is not included. I mean, some are easier to remove than others, but we are already very good at removing a very long list of elements in this way. So that brings us to already being able to remove half of the fission products today. And of course, we can implement that in a commercial reactor. And we also admit openly that removing the other half, it gets more and more difficult, and especially the lanthanides that I talked about. The lanthanides are the most difficult ones to remove, and we will not be able to remove those by the time we have the first commercial reactors available, but we can still have a breeder reactor without removing all the lanthanides. But of course, as we get better and better and remove more and more of those, we will get a better and better breathing ratio, and yeah. So this doesn't have to be fast, and it's probably not going to be. It's probably going to take more than a decade to be able to remove all the fission products.
Fission product separation is central to many molten salt reactor designs. What are the biggest technical challenges in implementing these separation technologies, and how mature are they today in terms of reliability, scalability, and regulatory readiness?
Ooh, that was a lot of questions on top of each other. So I would start with the last one. Where are we with regulatory readiness of processes that can remove fission products? So there has been a lot of research over the years in removing fission products, and it's sort of not super difficult because you can work with stable versions of many of the elements, so you can do the chemistry in your lab. And in many cases, you don't even need a glove box. You can do the chemistry in a fume hood. But because of the molten salts and because of the high purity we have to do all our experiments in a glove box. But this is something you can do. You don't even need special permits or anything because they're stable elements. But of course, at some point, you would have to do it inside a reactor. And that means the whole thing has to be approved by the authorities or the regulator in a given country. And there's only been, to my mind, there's only been 2 reactors in the history of mankind that remove fission products. That's the molten salt reactor experiment back in the 1960s, and then now there's a molten salt reactor running in China where they also remove. As far as I can figure out, they don't give a lot of data, but as far as I'm convinced, they remove also the volatile fission products, the xenon and krypton from that one. So those are the only reactor in history that remove fission products, and all the other solid fuel reactors, you basically cannot remove fission products. So clearly the regulators around the world are not really ready for this discussion, and there will be a learning process. But all molten salt reactors, whether they are thorium reactors or breeders or whatever they are, will remove the volatile fission products. And so I think the easiest part is in the beginning, where it's volatile. Later on, when we do more and more chemistry to remove the lanthanides or rare earth elements, this might also become more difficult. But yeah, don't worry. I think this will be resolved because of all the positive. I mean, this is basically what makes the waste profile of these reactors much better. And of course, everybody wants reactors with better waste profiles, because otherwise you have to do this process in in a different location. And basically in France, they have Le Hague that are doing this today, but they don't really separate the fission products. I mean, at least not in the way we do it. But they got their whole facility license, so it can be done, but it's I'm just trying to say it's not a walk in the park.
What in-house technologies and validation testing are being developed to take MSR toward commercial operation?
So we made the reactor design of our Thorium Molten Salt Reactor, I would say 8 years ago, more or less. And then, of course, we had to do a lot of simulation and calculations and sort of refining the design over the years. And we will continue to do that. But I would say the design is more or less frozen now. It's more about building the first design and testing it. There's a lot of test activity going on where we try to validate pumps and valves and heat exchangers and sensors and so on. And the thing is, it's not enough just to validate that it works in the best case scenario. You also have to see what happens if the temperature is a little bit higher or a little bit lower, or the flow rate is different than the ideal case. How does the whole design then behaves? So we need to do a lot of testing, and we need to validate that the test results are in agreement with all the calculations and simulations we did ahead of time. So it's a lot of work to do all that testing and all these special cases or combinations of different outliers.
What is the current status of primary circulating pump development and high-temperature salt testing?
Yeah, so it's true that the most critical component in a molten salt reactor is the pump. There is already sort of heat exchangers on the market you can buy. Maybe they've not been licensed for nuclear operation, but I mean, they exist. But the pump is a thing that needs to be developed. And we started really early on, 10 years ago, developing our type of pump, which is a different type of pump. It's called this type of pump is called a cant rotor pump. And many of the other companies that produce pumps for molten salt reactors, they make a type of pump that are called a cantilever type pump, which is a different design. And no matter which one, ours or the others, you need to do a lot of testing to make sure that it works, also in all these special cases. And we've been doing that now for, like I said, almost 10 years. And we've built more than 120 pumps and tested those. But that's a small version of the pump. That cannot be used for a commercial reactor. It's too small. It's meant for test reactors and test loops. But it still works really well. And I think we have shown many times that our design works, and it has run for many more testing hours than some of these other designs that I talked about, the cantilever type pumps. I hope that these other pump companies will eventually also have lots of pumps and lots of testing hours where it's working. But I also have to say that it's not quite ready for commercial reactors yet. But in any case, Copenhagen Atomics also want to run the test reactor first. I mean, that's 2028. And the pump we have now is already good enough for the test reactor.
In conventional water-cooled reactors, LOCA is a dominant safety concern. However, molten salt reactor is often described as inherently immune to LOCA. What design features fundamentally eliminate this risk?
Yes, that's true. So when you have a classical solid fuel reactor, which is let's say a light water reactor, the water coolant is really important. If that were to, and in a light water reactor, or pressurized water reactor, that water is under high pressure because that is what gives that reactor its efficiency. But the problem with high pressure is that if there is a hole somewhere in the circuit and all that high pressure water evaporates into steam, then suddenly in a short amount of time, you lose all your cooling. And that's what is called loss of cooling accidents. Then you can no longer cool your solid fuel rods, and then they tend to overheat from the decay heat. At that point in time, your reactor is already shut down. There's no more chain reaction. But because of the decay heat cannot get away from those solid fuel rods, then they melt, and that's what's called a meltdown. And meltdown has never killed anyone, ever. And it's also unlikely to ever kill anyone. But it's very expensive to clean up because the whole thing melts, and then you have sort of a pile of molten uranium at the bottom of the reactor core, and that's super radioactive because it still contains the fission products and the plutonium and so on. And it takes many, many years or decades before you can clean it up, and that's also the case both in Fukushima and Chernobyl. But I want to stress that this has never killed anyone, and it's unlikely to kill anyone. But the problem, of course, is all the steam that was released. It's released somewhere, so it flies out and maybe follow the wind, and it can travel hundreds of kilometers. And that steam usually contains radioactive particles, and this means that your radiation can be spread over a very large area, and that scares people. But it's not going to kill anyone. Well, when I say it like that, it could kill a few people in the close area of the nuclear power plant. But that steam is not going to carry a very large amount of radiation. So far away, like hundreds of kilometers away from the power plant, it's not going to kill anyone. But of course, it will make the ground radioactive, and that's, people don't like that, and I fully understand that, and we should avoid that. But I think the fear in the general public of meltdown is a big overreaction. So that being said, I also want to explain how this then works in molten salt reactors, because we do not have solid fuel rods and we don't have water under pressure. So we cannot have that same type of meltdown that the light water reactors can have. And therefore, a lot of people will say, ooh, it's a very safe reactor because it cannot have a meltdown. But it's sort of a little bit fake, because the old reactors are also safe and they're not going to kill anyone. But the accident scenarios in a molten salt reactors are different. And you still have this molten salt that has decay heat. So it will keep on being very hot. And you can be in a situation where your first containment, that means your first barrier around the salt, would melt, and your salt would drip out into the second containment. Most molten salt reactors that I know of have 3 and even in some cases 4 barriers. And I believe that it's highly unlikely that the salt would be able to melt through all those 4 barriers. But of course, that depends on the design, and I cannot say for any design. But the way we have made our design in Copenhagen Atomics, it's highly, highly, highly unlikely that the salt would be able to melt through several layers, and therefore it is super safe. And we don't have this steam that we release. And we do have some fission products that have been removed. For example, I talked about the xenon and krypton before. So if there was a hole in the reactor somewhere, those xenon and krypton could escape. But they are even less likely to pollute people sort of 200 kilometers downwind from the power plant. So even if they escape out of the building, which is unlikely, they're not likely to cause large areas of land to be contaminated. And those are some of the reasons why we believe molten salt reactors are less likely to cause problems. And obviously they cannot melt down in the same way as the old reactors, but you cannot, some people on the internet state that they are completely safe, they can never have accidents. That's not true. But the likelihood that they will kill anyone is significantly lower than traditional reactors.
With the SHANTI Act opening up private and foreign investment in India, how do you see the strategic opportunity for deploying your reactor technology in India?
Yes, so that is actually, I think it's very exciting times that India has now have this SHANTI Act coming out in late 2025, and it opens up for collaborations with private players in the nuclear sector or the nuclear industry in India. So if we look at the whole world, I mean, the 3 biggest countries in terms of installing nuclear reactors are US, India, and China, but Russia also plays an important role. India has not installed that many reactors in the past, but everybody expects a huge growth in nuclear reactors in India. And the government said that they wanted to install 100 gigawatts of new electric capacity before 2047. And I don't think this is possible if it was only the Indian government. I think this is, I find it highly likely to happen because they now open up for commercial players in the nuclear industry. It's still not 100% clear what it means. I mean, there's still some limitations in how much of this nuclear technology you can get from abroad outside of India. And there's also a question of, can the technology be owned by a company that is located outside of India, but in case the technology is manufactured or built in India, is it then, okay, there's some uncertainties about how exactly this SHANTI Act will play out in real life. But I do believe that it's a very important step. And I think for us, at least, we see this as a defining moment where suddenly India, you can say, bent the curve and starts to install maybe 10 reactors every year going forward. And this will, of course, have a huge impact on the Indian economy, but also make them maybe second or third largest nuclear company in the world, or country in the world.
Copenhagen Atomics is projecting an electricity cost of around $9 per million units at 90% capacity factor. Could you break down the key cost components behind this estimate?
Yes. So I want to start and say there's a lot of misunderstandings. Some people think that the reactor that Copenhagen Atomics is developing is a small modular reactor, not very different from the other small modular reactors. That's not true. Some people believe that it's a generation 4 reactor and it has the same technical specifications or capabilities or whatever as other generation 4 reactors. That's also not true. I happen to believe that our reactor design is further away from any other reactors. I mean, if you were to plot all the different reactor designs, all the ones that we built before are sort of in one cluster over here, and Copenhagen Atomics is very far away from those in terms of, no matter what you look at, I mean, the amount of fissile inventory to start them, or neutron economy, or cost, or size, or anything. And it's because we have developed something that is completely different and new, and it has a different neutron economy than all the other reactors. And that's also why it can run on thorium in thermal spectrum. I mean, we haven't had any other reactor that could do that reliably. So if you go back many, many times in history, people have added thorium to an existing light water reactor or some other existing reactors. And of course, what we saw was that it didn't improve the neutron economy. It also didn't improve the cost of electricity. And that's why it didn't continue, because, if there's no positive effect, why would you keep on adding thorium to your light water reactor? And the only reason, or the only way you can make thorium a better fuel than enriched uranium is if you can get to a breeding stage or very close to a breeder. So either just below isobreeding or, of course, above isobreed. Isobreeding means that you breed exactly the same amount of new fuel as what you burn all the time. And no reactor in history has been able to achieve isobreeding and basically reloading its own fuel. And I think we will be the first reactor to do that. And that also tells you that this is a completely new type of reactor that has never been invented before. It has been discussed many times, but nobody has been able to actually build one and make it work. And I think we will be the first one to do so. And this means that our fuel economy is completely different, and our neutron economy is different, and our burn-up simulations or burn-up capabilities are completely different than any other reactor ever built. And this is what makes the fuel economy better, and that means we, in a classical, or not even a classical reactor, I mean also the generation 4 reactors and the small modular reactors and whatever they call it, advanced reactors, all of those, you have to reload fuel, new fuel, again and again and again. And of course, they can buy a little bit more expensive fuel, and then they might not need to reload fuel every 2 years, then they can reload every 4 years. But because the fuel is much more expensive, it doesn't give you better electricity prices. But in our case, like I said before, we can use the same fuel for 100 years. And what we need to add to that fuel is just thorium. And thorium is not very expensive. It costs around $50 per kilogram. And each kilogram of thorium, we can get more energy out of each kilogram than if you were to use enriched uranium, for example. And enriched uranium costs right now around $4,000 per kilogram. So the fuel cost, we are much cheaper than any other reactor, including fusion. Then you can talk about the reactor unit itself. Is that less expensive than the other reactors? It is less expensive because it's much smaller. It is less expensive because it's much smaller. It's roughly the size of a 40-foot shipping container. And in that form factor, it can generate 100 megawatts of thermal energy. And this is very competitive with the other reactors. On top of that, it doesn't use pressure. So what makes most of the other reactors super expensive is that they run at high pressure, but we don't do that. So the materials we need for running the reactor is also less expensive. Both it's smaller than traditional reactors, and the materials used are less expensive. So this means that the reactor unit itself can be mass manufactured at low cost, and we can sort of have a gigafactory just builds more than one reactor every day. And this is part of why it's not super expensive. Also, the amount of fuel. So in any given reactor design, you need some amount of fuel to make it go critical. And that amount of fuel that we need is also smaller than for most other reactors. I would say even maybe all other reactors, because it's not only the amount of fuel, it's also the enrichment level. And we can run our reactors on 5% enriched uranium, and we only need roughly 2 tons of uranium to get the reactor going. And that's, many of the other reactors, they need 100 tons or 200 tons. So you see, it's not a small change, it's a big difference in the amount of fuel we need to get started, how long we can use that fuel, how big the reactor is, and how expensive the materials are for that reactor. So there's many items that makes our reactor less expensive. And also on the safety level, some of the safety components in the light water reactor is super expensive. And we usually joke that just one main coolant pump in a traditional light water reactor is more expensive than our entire reactor container. So the whole thing in our case is less expensive than just one pump. And typically these light water reactors need 4 of those pumps. And of course you can make a small modular reactor, and maybe the pump becomes a little bit smaller, and maybe it's half price if you make a small modular reactor. But it doesn't really change the electricity price in the end, because some other things also becomes more expensive. But in our case, it really affects the electricity price because everything becomes less expensive and smaller and easier to transport and buy and so on.
Thank you for your time today. As a closing thought, do you have any final words or a specific message you would like to leave for our audience in India?
Yes. So we saw back in the day when the airplane was invented, the whole world changed a little bit because now you could travel around the world in an airplane instead of what was used before, horse carriages or boats. And also when the automobile was invented, the world changed. When the computer was invented, the world changed. So there was a number of inventions in the past that changed the way the world functions or operates, and it changed the world forever in the future. And those changes doesn't come super fast. When the mobile phone was invented or transistor or the airplane or the TV or whatever, it took a number of decades before it really started changing the world. And I think our invention here of these molten salt reactors running on thorium is the same. It's something that will completely change the price of energy in the future, and it will make all products everybody consumes everywhere in the world cheaper, because in the end, all products need energy to be manufactured and transported. So if the energy needed for products are much lower cost, then products will also come down. And of course, the countries that adapt this technology first movers will be the first one to feel the advantage of using that new technology. But I think eventually most countries in the world will use this technology because it's such a game changer in terms of getting access to low-cost energy. And I think India has a unique opportunity because India does not have easy access to enriched uranium, but India has lots of thorium on the beaches, for example, and therefore India can really scale up thorium energy faster than maybe some other countries. And also the benefit for India is much bigger because India has a young population. And this means if you have access to a lot of energy, then you can grow your economy. India could easily double or triple their GDP, meaning that everybody in India would double or triple their salary. And this is more likely to happen in India than in most other countries in the world. I'm from Europe. In Europe, we cannot do that. We already have very high cost of labor, and we have quite old population. So it doesn't help as much to add cheap energy to Europe. It would help, but not as much as India. So I think really India is one of the places where this is likely to break through early, in the early phase, and then maybe later on it will be adapted by Europe. So we are a couple of people from Copenhagen Atomics that will be in Mumbai in the end of May 2026 for the Indian Nuclear Energy Forum conference there. I hope we can meet many people who are interested in advancing nuclear energy in India, and I really see a huge opportunity in collaborating with companies and individuals locally in India for providing our technology to the great country of India.